pick up where we left off. Just quick review. So this section is on the fundamental theorem of calculus. We saw hopefully what you thought was some really cool stuff yesterday. If nothing else, it's a gigantic shortcut that if you can find an antiderivative, makes finding areas using rectangular slices a little bit obsolete and way too tedious. Okay? But again, it depends on finding an antiderivative. So we started off by talking about area functions and just kind of developing that idea and using a definite integral to accumulate area. And then we were kind of taking this generic function big F of x, and we found the derivative of that, and we found this. That the derivative of big F of x was little f of x. So whatever function created the shape in the first place, if you were trying to accumulate area, and you found the derivative of that, you end up right back at the original function, which means that integrating and differentiating are inverses of each other. So we came up with this really simple way of finding the derivative of an integral, and we just said, well, the derivative of an integral is just the integrand with the upper limit plugged in. So whatever this function was right here, you just plug in the upper limit. That was provided that the lower limit was a constant and the upper limit was just a plain old x. So we did a couple of examples right here. And then we said, well, what if the upper limit wasn't an x? What if it was a function of x? Okay, and we answered that in a really roundabout way, and we really haven't gotten done answering that because we went through and we found this part right here, which is kind of the cool part, or the nice and useful part of the fundamental theorem of calculus. It's called the evaluation theorem sometimes. It means we can evaluate a definite integral using antiderivatives. So find an antiderivative for the integrand, plug in the upper limit, then plug in the lower limit, and then subtract the two, and that's going to give you the net area. Okay, but again, you've got to find an antiderivative. So we went through and we did several problems that we've done before. We got the exact same answers, but it was much easier now because we've got this really cool tool where we can evaluate definite integrals by using the antiderivative. We also talked about why you don't need a c on the antiderivative, because what you end up doing is you end up adding it in and then subtracting it out. Okay, so you just need that generic antiderivative. Okay, we put the two parts together. This is the part that says the relationship between integration and differentiation, they're inverses of each other. And then we said that we can evaluate a definite integral by using antiderivatives. So those are the two parts of the fundamental theorem of calculus. Hopefully you took time to read page 393 and 394. Again, to put this into kind of historical perspective, there is a ton of information there, and we did in a matter of a couple of days what it took people thousands of years to figure out. Okay? So to gain an appreciation for how powerful and how cool this tool is, you really do have to go through that slicing and summing process in order to appreciate that. I'll draw your attention to this again. This will be a question on the test. Please know the answers to this. Those four things right there are the answers to the question, what is calculus? Calculus is the mathematics of change. Derivatives describe rates of change. Integrals describe how those rates of change accumulate. And integration and differentiation are inverses of each other. Okay? If you know those four things, in a nutshell, in four very simple, concise statements, that's what calculus is. Okay? So we then went through and we did a couple problems using antiderivatives, one of which it was a little bit tough because we had to manipulate it to some extent in order to figure out what the answer was. You do have to be very careful when finding antiderivatives because that's in general quite a bit more difficult than just differentiating. Okay? It's a fair amount more complicated. We left off on this problem right here. We found that right there. And again, we could clean this answer up and we could clean that answer up a little bit, get rid of the negative exponents and so forth. Let's go ahead and do this problem and then we'll finish up the lecture on this section. So here's what we've got. We've got the definite integral from 1 to e squared 1 over theta d theta. So again, here's the integrand function. It's a function of theta. There's our differential. This literally has an interpretation. These would be the heights of each one of those rectangles, and those would be the widths of each rectangle. That's why that d theta or dx or dy or whatever it happens to be is important. Okay, so we need an antiderivative here. So I need an antiderivative of 1 over theta. Can I use the power rule on this one? Or the anti-power rule on this one? Nope. Okay. What is the antiderivative of 1 over theta? Okay, so we're going to do ln of theta. Technically, we'd need absolute value on this, and then we'd evaluate from 1 to e squared. I don't really need it on this one because the interval that we're interested in is all positive, so it's not that big a deal. So we're going to end up with the ln of e squared minus the ln of 1. And then I just need to know how to evaluate this. This would be a perfectly good test question without the use of a calculator, because those are things that you ought to know. What's the relationship between ln, log base e, and exponential base e? They're inverses of each other. So this is a 2. And what is the ln of 1? 0. Okay, so the answer on this is 2. So as ugly as this looks, and as weird as those limits of integration look, the answer to this is pretty darn easy. So if we were to take this, so let's think geometrically about what's going on here. And we integrated from 1 to e squared. So that's 1 and that's e squared. This stuff right there, that irregularly shaped area, that signed area, that net area between the curve and the x-axis is positive 2. Exactly positive 2. Yeah. Oh, I'm thinking of ln. Yeah, you're right. You're right. So here's what I was thinking of, the antiderivative. Here's what we're after. Okay. So this area right here. Yep. I was thinking of graphing ln. Yeah. So 1 over theta would look like this. Okay. And we're only interested in this part right here, this little portion right here. Thank you for catching that. Okay. Any questions? Okay. So let's read through this paragraph and let's come back to where we started this whole question. So we've already established that integration and differentiation are inverses of each other. Okay? So the derivative of an integral is the integrand with the upper limit plugged in. And we pointed out that that only works if the lower limit is a constant and the upper limit is a plain old x. Okay, but what if it's not a plain old x? What if it's an x squared? What if it's an x cubed? What if it's an e to the x? What if it's some weird function of x? How would we find the derivative of an integral then? Okay, so we said we'd answer that question, and we have gone about it in a very roundabout way. That was yesterday at about 10:20, I think, that we asked that question. And we did all that cool stuff in between. Well, we're now ready to answer that question. But in order to do that, let's just remind ourselves of how the chain rule works. So if I were to simply ask you to find the derivative of sine of x squared. Derivative, just the derivative of sine of x squared. Well, the outside function is sine, the inside function is x squared, so the derivative would be cosine of x squared times 2x, right? Derivative of the outside, leave the inside alone, then times it by the derivative of the inside. And we'd normally slide that out front, so we'd have 2 cosine of x squared. If we wrote it down in general, this is what we'd have. The derivative of the outside, leave the inside alone, times the derivative of the inside. So that's how we wrote it in prime notation. So what if we had something like this? Now the only difference between this problem, the derivative of this definite integral, and the derivative of the definite integral that we were doing yesterday, is that the upper limit used to be an x, now it's an x squared. So how do we find the derivative if the upper limit is a function of x? So let's go about it this way. Let's do it in little pieces. Let's find the antiderivative. Well, it's a generic function f of t, so its antiderivative would be big F, right? So the definite integral from a to x squared of f of t dt would be big F of the upper limit minus big F of the lower limit, right? So then if I were to slap a derivative in front of this, so this side is an equation, this is an equation, this is something that we're familiar with, we've seen this before. What if I then differentiate both sides? It's an equation, I should be able to do the same thing to both sides, right? So if I differentiate this side and differentiate this side, this is going to be the derivative of big F of x squared minus big F of a. Well, the derivative of big F of x squared. Well, the outside function is big F, the inside function is x squared. So if I find the derivative of the outside and leave the inside alone, the derivative of the outside would be little f. Leave the inside alone, that's x squared. You with me so far? And then what? 2x. Derivative of big F is little f. Leave the inside alone. Left the inside alone there. Times the derivative of the inside. Derivative of the inside is 2x. And what's the derivative of big F of a? If a is a number. This is just a constant, isn't it? So its derivative would be 0. So derivative of the outside, left the inside alone, times the derivative of the inside. I suppose if I wanted to, I could do this. I could do f of a times the derivative of a, which is 0, just for uniformity's sake. But that's still going to give me a 0 right here, isn't it? Okay. But again, this part right here is due to the chain rule. And the reason that's a 0 is because of the constant rule. Okay? So if we were to put a phrase to this, or we were to put notation to this, the derivative with respect to x of the definite integral from a to u, where u is a function of x, it's going to be f of u. We're going to take the integrand and we're going to plug in the upper limit, and then we're going to times it by the derivative of the upper limit because of the chain rule. So here's how we'd put it in terms of symbolically writing it down. And then if we said it in a phrase, it would be the derivative of the integral is the integrand with the upper limit plugged in times the derivative of the upper limit. And the reason we've got to times it by the derivative of the upper limit is because of the chain rule, because we were plugging a function into a function. This is a composite function right here. So again, that's due to the chain rule. So if you flip the page over, these problems are very similar to the problems that we had yesterday. In fact, I think I have exactly the same integrand and the exact same lower limit on each one of these as we did before, except for now, the upper limit is now a function of x. So if I'm going to find the derivative of this definite integral, so I'm going to find y prime, the derivative of an integral is the integrand with the upper limit plugged in. So that's going to be e to the x squared sine of x squared times 2x. So here's the fundamental theorem of calculus at work. When you find the derivative of the integral, you just take the integrand and you plug in the upper limit. Okay, there's the chain rule at work, because what we plugged into that function, what we plugged into that definite integral, that accumulating function, that area function, was itself a function of x. Okay? So this right here would be the answer. If I do this one, the derivative of an integral is the integrand with the upper limit plugged in. So that's going to be the tangent of x squared plus 2 times the tangent of x minus 4 times the derivative of the upper limit. So I need to take that entire expression right there and I need to multiply it by the derivative of the upper limit. And what's the derivative of tangent x? Secant squared x. Okay? So there's the answer on that one. Okay? Okay, but again, this relies on the fact that the lower limit is a constant and the upper limit is a function of x. So let's deal with this completely. What if the lower limit wasn't a constant? What if we wanted the lower limit to be a function of x also? We wanted it to be a variable. So we could not only change the ending point of where we stop accumulating area, but we could vary where we start. We could have a function tell us where we start adding up area and a function tell us where we stop adding up area. It couldn't get any more complicated than that, right? That would cover all the cases. The lower limit is a function of x, the upper limit is a function of x, and then we've got this integrand function that makes the shape where we're adding up area, right? So, see if you can figure this out. So this is what I've got represented here. I've got represented the definite integral from u to v. Those are both functions of x. So I'm going to find the derivative of an integral. Well, if we do it piece by piece, I could anti-differentiate this. I'd get big F of V minus big F of U, and then I'd differentiate. So do you have any idea what would go over here? There we go. F of V, little f of V times dv dx minus f of U du dx. No, not bad at all. And the cool thing about this is, and this is the awesome thing about, I mean, we're doing a bunch of math. We don't really have many numbers here. This is a bunch of theoretical stuff, very abstract. Okay, but the ideas are very cool because they all work together perfectly. So all the things that we learned in chapter 3 about differentiation still apply to this. All of the stuff that we've worked with so far in section 5.3, derivative of an integral is the integrand with the upper limit plugged in, period. If the lower limit is a constant and the upper limit is just a plain old x, that's still going to work here, and it's kind of swallowed up in this all-encompassing statement about how you differentiate an integral, about how derivatives and integrals are related. So if I were to write it symbolically, this is what I get. If I were to write a phrase, this is what I'd have. The derivative of an integral is the integrand with the upper limit plugged in times the derivative of the upper limit minus the integrand with the lower limit plugged in times the derivative of the lower limit. Now that's a mouthful, but for stating the relationship between integral calculus and differential calculus, that's not too bad. That's pretty darn succinct. So let's take a look at this problem right here. We've done this before. It was very easy before. All we did is we took the integrand and we plugged in the upper limit. Okay, let's get the exact same answer by using this all-encompassing statement about the relationship between integration and differentiation. So the derivative of an integral is going to be the integrand with the upper limit plugged in. So that's going to be, e to the x sine x times the derivative of the upper limit. What's the derivative of the upper limit? 1. Minus the integrand with the lower limit plugged in, so that's going to be e to the 5th sine of 5 times the derivative of the lower limit, 0. So what do I end up with? I get the same thing I got before with a simplified statement of just finding the derivative of an integral. You just plug in the upper limit into the integrand, okay? But now we can deal with more complex derivatives of integrals, more complex problems like this. So let's take a look at this one. So the derivative of an integral is the integrand with the upper limit plugged in. So that's going to be e to the x cubed times the derivative of the upper limit. So that's going to be 3x squared. Minus the integrand with the lower limit plugged in. So that's going to be e to the ln of x times the derivative of the lower limit, which is 1 over x. And then we're going to clean this up just a little bit. So this is going to be 3x squared e to the x cubed. These two undo each other, so this is just an x times a 1 over x, so that's going to be a minus 1, and that is the answer. Now, I would venture to guess that there are plenty of people that have taken calculus, that if you gave them this right here, unless they really understood this fundamental theorem of calculus, unless they really understood the way differentiation and integration are related to each other, and how we still, if we're differentiating, you still have to carry out the chain rule, there are lots of people that would struggle to get this answer. I'm hoping after our discussion here, it should be relatively easy, even though for most people this would be absolutely mind-blowing that you can do this problem. So let's take a look at this one. Same type of thing. Best way to keep it straight is just that phrase, or if you like memorizing symbols, that right there. So we've got a derivative of an integral. So that's going to be the integrand with the upper limit plugged in. So that's going to be the sine of x squared times the derivative of the upper limit. That's going to be 2x. Minus the integrand with the lower limit plugged in. So that's going to be the sine of e to the x times the derivative of the lower limit. So that's going to be e to the x. If we clean that up just a little bit, which we should, we're going to end up with something that looks like this. But that's it. That's the answer. Any questions? It's not too bad, is it? Relatively easy? Okay. You have some problems in your textbook that do something like this, but you will not, in fact, I don't think you'll find this in your textbook. In fact, there are not very many textbooks that go through this complete idea. It is, I mean, it's complicated, but it's pretty darn amazing. The cool thing about this is if you understand that one theorem in that way, we can take this problem and we can do this several different ways. In my opinion, the easiest way to do this problem is using that statement that we just talked about. So we're going to do this 3 different ways. We're going to use inverse operations. These 2 functions, these 2 operators is what we call them, they undo each other. Differentiating undoes integrating. How are they related? Well, you just take the integrand and you plug in the upper limit. So that's going to be 1 over 10 squared plus 1 times the derivative of the upper limit, which is derivative of the upper limit.
Would it be 0? That 1 over. Okay.
You with me? The derivative of an integral is the integrand. Okay, if I needed to, I could write that with the dz on the end. Maybe that makes a little bit more sense. You good with that? Integrand with the upper limit plugged in times the derivative of the upper limit. Derivative of the upper limit, since it's a constant, is 0. You with me there? Minus the integrand with the lower limit plugged in. So this is going to be x squared squared plus 1 times the derivative of the lower limit. So that's going to be 2x. Any questions? Yeah.
Why is it a 1 on top?
Yeah.
So there's a dz here. Where do we normally write the dz?
This side.
On the end. Whoops, dz. Okay.
Oh, so it's just 1.
What's always up there? There's always a 1 up there. Okay. Is that all right?
Yeah.
Any questions? Very good. Okay, let's clean this up just a little bit. This is going to be a 0, so that's gone. If I clean this up, this is going to be a negative 2x on the top, and this is going to be x to the 4th plus 1 on the bottom, and that right there is my simplified answer. If you differentiate that definite integral, this is what you get. Notice that we've reversed the roles here. The constant is the upper limit, and the variable function is the lower limit. That's a little bit weird, but the cool thing is this statement right here handles it. Just fine, no problem. Any questions there? Okay, I'm going to change colors and we're going to do this using properties of integrals. So I'm going to take this right here, and we normally don't have a constant as the upper limit. That's normally the lower limit. So I'm going to rewrite this. I'm going to write d dx integral from 10 to x squared, and I'll write it this way, 1 over z squared plus 1 dz. Now, can I just do that? I need a negative. I changed the order of integration. Okay, stop and think about this. I have no idea where x squared is. Is it to the left of 10 or to the right of 10? It doesn't make any difference. Okay, this handles it just fine. And I also know, using the properties of integrals, if I change the order of integration, if I go from x squared to 10 and then switch it from 10 to x squared, I have to change the sign of whatever the answer turns out to be. Is that all right? Okay, so this is going to be the integrand with the upper limit plugged in. So there's going to be a negative here, because that negative right there, I could leave it out front or slide it up on the top. X squared plus 1 times the derivative of x squared, so 2x. Okay, do I need to bother with the rest of this stuff? I could if I want, but because that is a constant, its derivative is going to be 0, so that's going to wipe out that term. So I'm going to end up with, this is negative 2x over x to the fourth, whoops, plus 1. Same answer as I got over here, right? Yeah.
So let's say the bottom wasn't a 10, and so the 0 wouldn't cancel out. Would you want to put the negative immediately there, or would you wait till the very end and then make the whole thing negative? So like in there, you put the negative, and you like plugged in the negative.
It really would be personal preference. Like on this one, I mean, if you wanted to pull the negative out front, find that, and then distribute it through, that would be okay. If you wanted to put it right here, that would be okay, which is kind of the way I thought of it. Okay. So this would be minus a minus. That's going to have a plus on it. Is that all right? Good question. Okay, everybody good with that? Okay, let's do it one more way, and let's show that this actually matches up. Let's find the antiderivative. So let's look at this right here, and this is what we're after. We're after the derivative with respect to x, the definite integral from x squared to 10, and I'm going to write it this way, 1 over z squared plus 1 dz. So I've got to find an antiderivative for this. Does that look familiar to anybody? Tangent inverse, okay? So here's what I've got. I'm going to find the antiderivative, and I'm going to evaluate this definite integral. So this is going to be tangent inverse of z evaluated from x squared up to 10. Is that okay? We in good shape? Okay. So that's going to give me the derivative with respect to x of the tangent inverse of 10 minus the tangent inverse of x squared. Is that okay? Just doing it a piece at a time. We did the anti-differentiation. We'll evaluate it at the upper limit, subtract what we get when we evaluate it at the lower limit. So here's what I'm going to find. I'm going to find the derivative with respect to x of the tangent inverse of 10 minus the derivative with respect to x of the tangent inverse of x squared. That's what I'm after, right? I can differentiate term by term. What is this? Tangent inverse of 10 is a number, right? So this is a constant, so its derivative is 0, okay? Minus whatever I get for the derivative here. Let's see, tangent inverse. Well, gosh, we just got done anti-differentiating it, so we better know what the derivative is. The derivative is 1 over whatever we were taking the tangent inverse of squared, so that's going to be x squared plus 1, times the derivative of whatever we were taking the tangent inverse of, so that's going to be 2x. So look what we get here. Negative 2x on the top, x to the fourth plus 1 on the bottom, and it's exactly the same as doing it those other two ways. Okay? If that isn't evidence that all these mathematical theories and everything fit together perfectly, we just did a very, very complicated problem, 3 separate ways, and got exactly the same answer. Now, which one was the easiest? I think that was the easiest, wasn't it?
Yeah.
Because that fundamentally captures the relationship between integration and differentiation. They're inverses. And we're differentiating, so we better carry out the chain rule. Make sense? Okay. All right. So we've got a couple more problems that we want to take a look at. The last one on the bottom of this page right here, it says, use the function below and the area function a of x equals the integral from 0 to x, f of t dt, on the interval from 0 to 17 for the following. So the first thing is we want to find the zeros of a. We want to find the zeros of a. We want to find the points on 0 to 17 at which a has a local maximum or minimum. So we want to find the extreme values. And we want to sketch the graph of a. Okay, so let's think about this for just a second. Okay. I want to sketch A. A is going to be this graph down here. I'm going to graph this area function here. This right here is a graph of f of t. How is f of t related to A? How is f of t, how is the function little f related to the function A if it's defined this way? Okay, the derivative of A. So if I found the derivative of this, if I found A prime of x, I'd differentiate this side and I'd end up with f of x, right? So this is a graph of A prime. This is the derivative. Yeah, but we don't have the function, so it'd be tough to find the antiderivative. We can approximate what it looks like though, right?
Yeah.
Okay, so here's what we're going to do. Okay, let's do this part first. Let's do part A. It says, find the zeros of the function A. A is an area function. So let's think about this. Okay, A adds up the area from A to whatever x is. So if I start at 0 and I start up adding area, what type of area am I accumulating here? A bunch of positive area. Okay? What type of area am I accumulating here? Negative area. Okay? Now, what's the first time that the area is 0? Now, don't say anything out loud and think about that real quick for just a second. We went over properties of integrals a whole bunch. This was kind of a cool property. We used it a couple times. When is the first time the area is 0? 1? When it goes from 0 to 0. So if I were to put a 0 right here, I'm not going anywhere. I'm not adding up any area. So where's the first time that A is equal to 0? At 0. Okay? Now, I'm accumulating a bunch of positive area. Then what happens? I start accumulating negative area. Okay, now if I stopped right here, I've got a whole bunch of positive area. So my area definitely isn't 0. Okay, and then I slowly chip away at it. What happens to the area by the time I get right here? It's at 0. Then I start adding up positive area again. Then I start subtracting area until I get to right here, and then I end up at 0. Okay? So what are the zeros of A? 0, 8, and 16. That's where the area would be 0. That's where the area function equals 0. Find the points on 0 to 17 where A has a max or a min. Kind of. Or stop and think about it this way. This is the derivative, right? That's the derivative. Okay, max and mins can occur when the derivative equals 0 or where it doesn't exist. Is there anywhere where the derivative doesn't exist? No. Okay? So maxes and mins would occur where the derivative equals 0. If you think about it, this is a graphical sine line right here. It's 0 here, it's 0 here, it's 0 here, 0 here, and 0 here. What's the value of the derivative here? Positive. What's the value of the derivative here? Negative, positive, negative, right? So what does that mean the original function is doing? Level, increasing, level, decreasing, and so forth, right? And this last little bit right here, it goes positive again, so again it's going to increase. So what we're going to see here, now put all these pieces together. Let's think about this for a second. We said that we were accumulating a bunch of positive areas, so the area was getting bigger and bigger and bigger. And then what happens when we get here? We start chipping away at it. We start subtracting from the area that we accumulated. So what happens is we go up, and then we start going down. and then we go up, and then we start going down. Now my graph isn't perfect, but do you get the idea? Let me make that look a little bit better. Okay, that's roughly what it would look like. So we can see that we've got a graph that leveled off. Whoops, let me change colors here. Graph that leveled off here, 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 and here. Whoops, and then it starts to increase again. Okay, and you can see that it was increasing, decreasing, increasing, decreasing, and so forth. Okay, so where does it have a max or a min? We'll do the maxes first, and we'll write them right here. The maxes occur at 4 and 12, and the mins occur at 0 and 8 and 16. Any questions there? Okay. And there's our sketch already completed. Okay. Ready for the last page? Okay. So let's take a look at this one. And this is where we kind of blend together the stuff that we've been talking about for a while. One of the usual applications for derivatives is finding the relationship between position, velocity, and acceleration. So what we're very used to doing is we're very used to doing this. We're going to differentiate with respect to t going this way, and we're going to go from position to velocity. If I differentiate again with respect to t, I end up with acceleration. Well, now what we can do is we can anti-differentiate or integrate. We can integrate acceleration and we can get velocity. And we can integrate velocity and we can get position. Any questions? Okay, so let's take a look at this problem. It says, suppose f is a differentiable function whose graph is shown. Okay, so here's f, little f. Suppose the position at any time t in seconds of a particle moving along a number line can be given by this. So here's our function. Now this says s, so what type of function is this? This is a position function, but the position function is defined as a definite integral of some other function. Well, what function would you have to integrate to get position? You'd have to integrate velocity, right? So this is a velocity graph. If you integrate a velocity graph, or in other words, if you accumulate position underneath the velocity graph, that area accumulated is net. Okay? We could say displacement, or we could say position change. Okay? Now, let's kind of blend all this together. If I have a velocity graph, if this right here is a velocity graph, then the slopes are acceleration. Okay? So the cool thing about having velocity is you can work with both branches of calculus. If you have the velocity function or the velocity graph, you can differentiate and you can get acceleration. You can anti-differentiate or you can integrate and get position. Okay? All right. So this says, what is the particle's velocity at t equals 5? Well, little f is the velocity function, so we're going to look at 5, and its velocity would be 2. Okay? And since this is in meters, and this I believe is in seconds, we'd probably say meters per second. Is the particle's acceleration at t equals 5 positive or negative? Answer there is negative. Why is that? Okay. Negative slope on velocity graph. What is the particle's position at t equals 3? What is the particle's position at t equals 3?
None.
What'd you say? 9 meters? Let's check. How would we check? Where's the position function?
That would be
Right here. So we want to find what is s of 3. In other words, we want to integrate from 0 to 3 f of x dx. So that means you want to find this area right here, right? It's a triangle, luckily, because we don't know what the function is. We certainly couldn't use antiderivatives. We want to find that area right there. 3 units wide, 3 units tall. It's a triangle, so that's going to be 9 halves. 9 halves meters. Yeah, S is in meters right here. Okay. At what time in the first 9 seconds does S have its largest value? When is the position the biggest in the first 9 seconds? It is 6. Okay? Now, it happens at 6 for the same reason that we talked about up above. Remember what we said happens here. This is the derivative of A. So what happens is we're adding up a bunch of area, or if you think about it, if this were a velocity curve, we'd be adding up a bunch of positive position change. Okay? Then we'd start going in the negative direction, subtracting from whatever position change we accumulated. So here's what we've got. If we've got a velocity curve, I'm accumulating a bunch of positive position change until I get to right there. Now, yes, I'm slowing down how much positive position change I accumulate, but right here, I get the most positive position change, and then what do I start doing right here? I start chipping away at it. Or in other words, the derivative of position, because remember, this is velocity, okay? The derivative is positive here, 0 here, and then negative here. So if I've got a position function that's increasing, leveling off, and then decreasing, that's going to happen when the derivative, or when in other words, when the velocity is 0. So at what time? 6 seconds. Okay, let's look at the next one. Approximately when is the acceleration equal to 0? Okay, about 4 seconds and about 7 seconds. So 4 and 7 seconds. When is the particle moving toward the origin, and when is the particle moving away from the origin?
puts it towards the origin from 6 to 9.
Okay, so let's think about this. Do we know where the particle started? How do you know it started at 0? This is a velocity function, so just because that's 0 right there. If you plug in a 0, this is the definite integral, the accumulated area from 0 to 0. So its initial position, if we were to think about what the position curve looks like, it would start at 0. And then it moves in a positive direction. So it's going to move to the right, accumulate a bunch of positive change. That's going to happen until we get to 6 seconds, right? Oops, let me slide that over. 6 seconds. And then when the velocity goes negative, it's going to turn around and go that direction. So positive velocity started at 0, positive velocity. It's going to move in a positive direction away from the origin for the first 6 seconds. So from 0 to 6 seconds. And then it's going to turn around and it's going to head back toward the origin from 6 to 9 seconds. Great question for G. On what side of the origin does the particle lie at t equals 9 seconds? Positive side, on the right side. Okay. Can you tell me why by looking at the velocity graph? Okay, very well said, even my verbiage there. Okay, we accumulated a bunch of positive position change, and then we chipped away at it a little bit, but this area is much larger than that area right there. So we're going to end up with a positive position. If we integrated from 0 to 9 on the velocity function, that would tell us our net displacement, our net position. Bunch of positive, little bit of negative. We're going to end up being positive, so it's going to end up on the right side, or in other words, the positive side, if we set up our coordinate system that way. Okay, any questions? Sure? Okay. Let's see. We've got 4 minutes left. I've kept you over several times already. I think what I'll do, I think I will record a video on this. This isn't completely necessary, and I'm not sure you have one on your assignment like this. This is a darn cool exercise. If you want to try it, I think going through and just following the instructions, I think you could do it. But I'll record a video on it. If you want to watch it, great. If you don't want to, that's fine. I really don't think I'd ask a question like this on the test, but it is a very interesting exercise. So we'll call it quits right there. If you want to watch that video, great. I'll get it uploaded probably later today, if not by Saturday at least.